Welcome. So in the study of curves in space and vector-valued functions, one interesting application occurs, and that is trying to find the curve of intersection for two surfaces. So we're going to look at an example here, and we want to find the curve of intersection of the surfaces x squared plus y squared equals 4, and z equals x times y. Now, we should recognize that first surface, x squared plus y squared equals 4, as a cylinder, where the central axis is the z-axis, and our cylinder has a radius of 2. The other surface is not any of the standard surfaces that we readily recognize. It is a standard surface, but not one that we readily recognize. So when we start to think about looking for a curve of intersection, we need a parameter, and we often use the parameter t. And one of the the fundamental basic strategies is just to let one of the coordinate variables be represented by t. So let's see what happens if we were to try to use that particular strategy. So for example, what would happen if we let x equal t? Well, then in our cylinder, we would have t squared plus y squared equals 4. And we could solve for y and substitute what we know about t and y back into z, and we would have a representation. So quickly, what would that look like? Well, y squared would equal 4 minus t squared. Then y would have to equal, taking the square root of both sides of that equation, plus or minus 4 minus t squared. So what you're seeing there is actually there are two representations of y, not a single. So what would happen is we would say, okay, so what if y equaled the positive square root? We get 4 minus t squared. Then our z would equal t times square root 4 minus t squared. If y equaled the negative square root of 4 minus t squared, then z would equal negative t times the square root of 4 minus t squared. So if we take that strategy, which is kind of the natural strategy, we kind of get into this situation where we have two separate functions that are necessary to describe this curve of intersection. We would need both of these functions to create our curve of intersection. And so what would that possibly look like? Well, we could have two curves. We'd call them perhaps R1 and R2. And these vector-valued functions, we would have our x component, which we said at the beginning of the discussion that x would equal t. Then we have two options for y, so we'll take the first one, the positive square root, so 4 minus t squared. And then the corresponding z value would be t times square root of 4 minus t squared. And then there's a second option from our second solution for y, and that would look something like this. T in our x component, for our y component, negative 4 minus square root of 4 minus t squared. And then our z component would be negative t times 4 minus t squared. And so those would be the curves necessary to describe the curve of intersection. But there's a better way. And ideally, we want a single curve because, well, first of all, because in our instructions, we were asked to find the curve. Well, I have two curves. The curve grammatically means there is one curve. And it's just more efficient and less prone to problems later on when in modeling and so forth. So let's back up just a little bit and remember that we said that this is a cylinder of radius 2. And so the cylinder is based off a circle, or can be based off a circle in the xy plane of radius 2 centered at the origin. And so maybe a better strategy would be to rely on the knowledge we have of trigonometry and how we can use trigonometric functions to model a circle. So if we think back to the unit circle idea, in the unit circle idea, we have x, the x coordinate, being represented by cosine of theta, and we have the y coordinate being modeled by sine of theta. And then we have the Pythagorean identity that says cosine squared of theta plus sine squared of theta equals 1. And that 1 is the radius of the unit circle. So if we're thinking about our cylinder here and just its presence in the xy plane, the radius of that circle should be a 2, not a 1. So what would happen if we took these ideas from the unit circle and multiplied by 2? Okay? Because we want the radius of our circle in the xy plane. We want that radius to be a 2 because 4 should represent radius squared. Well, then what happens down here is that we end up with a 2 cosine squared and a 2 sine squared. That no longer is equal to 1. That's going to give us a 4 cosine squared theta plus a 4 sine squared theta. And if we factor out that 4, we get cosine squared theta, that should be a squared, plus sine squared theta, which is 4 times 1. So this gives, so this can all happen in our minds, right? I don't necessarily have to write it all down, but I need to make this type of observation. So if I could let x be represented by 2 times the cosine function and y represented by 2 times the sine function, we now have a way of expressing our cylinder over here on the left in terms of a parameter. I use theta in my exploration, but I would use t to parameterize the curve. And all would work out. So let's take a look. So what we'll do is we will let x equal 2 cosine, and instead of theta, we're going to use t for our parameter, and y equal 2 sine t. All right, in our exploration, we notice that this parameterization does satisfy the equation of our cylinder. So if we do that parameterization, then z would be, in essence, 2 cosine of t times 2 sine of t, or 4 times cosine t times sine t. So then our vector valued function, or our curve of intersection, would be In our x component, we would have 2 cosine of t. Our y component would be 2 sine of t. And our z component would be 4 cosine of t sine of t. And that would give us our curve of intersection. So let's go ahead and take a look at what these surfaces look like and where that curve of intersection comes into play. So I'm going to go ahead and navigate to CalcPlot 3D. The URL is easily found by just Googling CalcPlot 3D. And so we're going to add to the graph. Now the first surface was a cylinder, and so of these options here, how do I enter that cylinder where it's not a function of x and y? Well, I come down here to implicit surface. I'm going to go ahead and delete what's automatically populates there, and I'm just going to type in x squared plus y squared equals 4, and go ahead and check that box, and there's my cylinder. And I'm going to then put in our second function, which was z equals xy, and that is a function of this form, so z equals something. So I'm going to go ahead and get rid of what's already there and enter xy, and that is my second function. And so we can see, as we let this rotate, we can see there is a curve of intersection, and notice the periodic nature of that curve of intersection. And if we had done the more algebraic approach, the first solution we came up with, we wouldn't necessarily have noticed this kind of oscillatory periodic behavior. But by using trigonometric functions to characterize that curve, we see for that curve of intersection, we captured the notion of oscillatory behavior. So let's go ahead and add in our curve of intersection. So we're going to add to our graph a space curve. And what I'm going to do is I'm going to put in what we determined. So I want 2 cosine of t. I want 2 sine of t. And for my z component, I will eliminate what's already there, and we'll have 4 cosine of t times sine of t. Hit enter and add that to the graph. So we can start to see that curve of intersection being highlighted on the surfaces we see. And then if it's a little bit too busy having both of those surfaces there and it's hard to see the actual curve, what we can do is we can turn off the 2 surfaces, and now we can see our curve of intersection. So let's take a look at one last idea here, and that is, of all of the infinite number of points that live on that curve of intersection, what value of t would provide the location of a specific point? In the case that I have here, we're interested in the value of t that would provide us the location of 1 square root of 3 square root of 3. And so what we want to remember is each of those numerical values is produced by the functions in the x component, the y component, and the z component. So what we can do is create 3 equations based on those functions in our curve of intersection. So that would look something like this. So I would have the equations 2 cosine t equals 1, 2 sine of t equals square root 3, And for cosine t, sine t would also equal square root of 3. So what I can do is choose one of the equations to solve and then verify that that solution satisfies the equations for the other two components. So I'm going to choose to focus here on the equation for the x component. And so if I divide both sides of that equation by 1/2, I end up with cosine of t equal, divide both sides of that equation by 2, I end up with cosine of t equals 1/2. And so there are actually, if I limit myself to 0 to 2 pi or the unit circle, there are two values of the parameter t that can produce a cosine of 1/2. Those two values are t equals pi over 3 and t equals 5 pi over 3. So we need to verify whether those values of the parameter t satisfy the original location on our curve of intersection. So we will want the y component to become square root of 3, and we would want the z component to also become square root of 3. So let's start by just confirming what happens when t is pi over 3. So substituting in pi over 3 for the y function, we do see that 2 times sine of pi over 3 will produce the square root of 3 that we wanted. Substituting in pi over 3 for our z component function and simplifying that, we do see that we get a square root of 3 for our z component, which is what we wanted. So t equal to pi over 3 does produce that location. We did have a second value for t, so we do need to verify whether or not that also produces the location we're interested in. Now, if we are verifying what happens with our second solution here, our 5 pi over 3, and we substitute that value in for our functions, what we'll notice is that when I substitute in 5 pi over 3, our sine function produces a negative square root of 3 over 2. So our y-coordinate is now square root of 3. Something similar happens here with our z component. So what we know is that this 5 pi over 3 is not a value of t that produces the location that we're interested in. The only value of t that produces the location that we're interested in is t equals pi thirds. I hope you find this helpful.